Hello. In this video, Derivative Rules Part 2, we're going to continue to look at some derivative rules. Now before we do, just to recap from last time, we're going to use our rules on a polynomial to calculate the following. So let's let fx be 3x to the 5 minus 3x cubed plus 1. We're going to find f prime x, we're going to find the equation of the tangent line at the point -1 and 1, and the equation of the normal line. So let's go ahead and do part A. Now remember before, this used to be very difficult. We'd have to do the 1, 2, 3 steps with the limit. But now that we have the rules, the derivative is simply equal to, well, 15x to the 4 minus 9x squared, and the derivative of 1 is just 0 because it's a constant. And again, that's very nice. It's very clean and quick. It's nice to have rules for derivatives. I actually find doing derivatives quite fun once you get the hang of it. So let's look at part B. Find the equation of the tangent line. So remember, we need a point and we need a slope. Now our point is given to us as -1 and 1. Then we need a slope. So m is going to be equal to f prime of -1. So we take that number of -1 and we plug it into the formula for slope, which will give us 15 times -1 to the 4 minus 9 -1 squared. -1 to the 4 will just be 1, so 15 minus 9, so that's going to give us 6. So we go ahead and do our formula. Y minus y1 equals m x minus x1. And you can put minus minus makes a plus. So there is your tangent line. Now for part C, we have this new word, normal. What is a normal line? Is it like a line that's not abnormal, but it's normal? It's a bit of a strange word in math. Normal means perpendicular. If you remember from physics, when you have an inclined plane, and you have some object on that inclined plane, well, there's this force that comes out of the plane. It's perpendicular to the plane. We call it the normal force. And that's because it makes a little right angle here with the actual surface. It's perpendicular. It's normal. Now to find the normal, we need to find the perpendicular. And to find the perpendicular, we need to remember how in the world that works. Well, there's actually a formula for it. If you want to find the perpendicular slope, it's always just going to be the negative reciprocal. Negative reciprocal. So whatever you had as your slope here, 6 for the tangent line, the normal line is just going to be the negative of this and then the reciprocal. So for C, our new slope is equal to -1 over 6, and we'll get y minus y1 equals -1 over 6 x plus 1. And there's our new equation for the normal line. Now let's take a look at Rule 5, the exponential derivative. We want to find the derivative of e to the x. Now, one prediction might be that it works sort of like the rule with the power. X e to the x minus 1. Maybe it's something like that, where the x comes down. But, I mean, if it was that, why wouldn't I have included it in the other rules? So maybe it's something different. Maybe, well, who knows? Feel free to take a guess, and then we're going to go ahead and calculate this. Now I'm going to jump right into the limit. So h approaches 0, e to the x plus h minus e to the x over h. Well, what can I do there? Is there any technique, any simplification? And in fact, there is. If you remember from exponent rules, if you have 2 to the 3 times 2 to the 4, you can make that 2 to the 3 plus 4. Usually we use the exponent rule in this direction, but we could use it in this direction. We could write this as the limit h approaches 0, e to the x, e to the h minus e to the x over h. Well, it looks like there's an e to the x in common, so we can factor that out. And we'll be left with e to the h minus 1 over h. Now, and this is pretty interesting here, e to the x actually factors out of the entire limit. Because there's no h involved, it's technically a constant with respect to h. And so constants we know factor out of limits. So e to the x comes out in front, and we have h approaching 0 of e to the h minus 1 over h. Now don't be fooled, this is still 0 over 0. Because if you plug in h equals to 0, e to the 0 is 1, 1 minus 1 is 0, over 0, we still have to do more work. And unfortunately, it doesn't seem like there's much work left to do. We've done a little bit of factoring, nothing's canceling, and we don't really see any way forward. And the problem is that you actually don't have enough information right now. This tricky letter E has not been defined to you. What is E? What in the world is that number? Sure, we know that E is approximately 2.71. It's a decimal number. It's similar to pi that way. But what is it representing? Where does it come from? What's its definition? If I was to say E equals something, what is it equal to? Well, in fact, E is actually a limit. And the definition for E is the limit, h approaches 0, of 1 plus h to the 1 over h. Now, there's no reason for you to believe that, because I just wrote down a crazy limit. But I'm going to show you on Desmos that this is indeed true. So here we have the quantity 1 plus h to the 1 over h. And we can see right away that if I try to plug in h equal to 0, well, I get undefined because I have 1 over 0 in the exponent, and that means that there's an infinity there and all sorts of issues. But if I take h as equal to 1, I have a value of 2. If I say make h equal to 0.5, I have 2.2. And as h approaches 0, that number begins to grow. It's 2.5, maybe 2.6, and I can make that number very, very close to 0. Well, it seems like the number above settles down. As h approaches 0, that number is getting closer and closer and closer to, well, I've got the reference point right underneath. We're getting 2.71821, and underneath the exact value for E is 2.71821, and so on. As I get closer and closer to 0, it is indeed true that this quantity becomes closer and closer to E. So in the limit, this is E. So hopefully that Desmos was enough to convince you that this is indeed true. And it's definitely worth writing down and putting somewhere in your notes, because it'll be a handy limit to know that E is equal to the limit as h approaches 0 of 1 plus h to the 1 over h. It's a very useful definition. And what we're going to do is plug that in here for E. So we're going to get here e to the x on the outside, the limit h approaches 0, 1 plus h to the 1 over h. That's being plugged in for E. We still have an h on the outside, minus 1 over h. Now again, I don't have to write another limit in front of this, because I'm limiting as h approaches 0 in the definition, and I'm also limiting as h approaches 0 here. So either way, h is approaching 0, so I only have to write one limit. Now let's go ahead and do some simplification. When we have a power to a power, remember, we multiply. So this is going to become equal to e to the x, limit h approaches 0, 1 plus h to the h over h minus 1 over h. Well, of course, h over h simplifies to 1, so let's keep going. We have e to the x, limit h approaches 0 of 1 plus h to the power of 1 minus 1 over h. Well, when something is to the power of 1, we don't really need to write it, which means that these 1s, plus 1 and minus 1, cancel out. So this is e to the x, the limit, h approaches 0 of h over h. Well, that cancels out. So we have e to the x, limit, h approaches 0 of 1, and the limit of a constant, it's just 1, which means there's the derivative, e to the x. The derivative of e to the x is equal to e to the x. Well, this is very strange. And one thing we need to notice right away is that all of this extra work here, was to work on the 0 over 0. So this quantity right here, this limit, gave us 0. We can remember this as another special limit. It's like the one with sine. If we have the limit h approaches 0 of e to the h minus 1 over h, that's going to equal 1. Definitely important to know that. It sometimes comes up when you're trying to solve problems. So that's definitely interesting for starters. But the second thing that I think is even more interesting is that when you try to do the derivative of e to the x, you work and you work and you work and you work, and in the end, you just get e to the x. So, as a remark, the derivative of e to the x is itself. The derivative is just e to the x. The way I think about this as an analogy is that e to the x, it's like a Pokemon, maybe like a legendary Pokemon, and d dx is a little Pokeball. And we try to throw the Pokeball at the Pokemon, and the Pokemon just pops right back out. It's not very effective. That's one way to think about e to the x. It's like a Pokemon that you just can't catch. No matter how many times you try to throw the derivative at it, it just always pops right back out. So let's try the derivative of 7e to the x. Well, the 7 is just a constant, so we can write that out in front. And the derivative of e to the x is simply e to the x. So just 7e to the x. Let's do the derivative of x to the 5 plus e to the x plus x. First we'll get 5x to the 4, then we'll get e to the x, and then we'll get 1. And there you have it. Again, these derivative questions are pretty quick once you learn the rules, and of course once you prove the rules. Let's try this one. We definitely need to rewrite this as a power of x. This is x to the 2 over 3. So we'll get 3 times 2 over 3, x to the minus 1 over 3, plus 11 e to the x. Now it's good form here to simplify, so the 3's will cancel and we'll get 2x to the negative 1/2, or 1/3 I should say, plus 11 e to the x. Let's go ahead and try a multiple choice question. Determine the derivative of f of x equal to mx plus b, where m and b are constants. I think the answer is A, B, C, or D. Go ahead and pause the video and give this a try. All right, well, if we think about this, the derivative of mx plus b, the derivative of mx plus b would be equal to, we can do the derivatives one at a time, and we'll know that the derivative, of course, of a constant like b is going to be 0. For the m comes out, and the derivative of x is 1, so we'll just get m times 1, which is m. So the correct answer is B. Now, we don't actually have to do all this work, because if you think about it, this is the equation of a line. The derivative is asking you for the slope of the tangent line. Well, on a line, the tangent line is just the slope. You don't even need to do a tangent line to find the slope of a line. You just look for the slope. So by asking for the derivative, I'm really asking for the slope of this line. The slope of this line is just m. So you could do the answer without even having to do any calculus, which is kind of neat. Let's try another one. Determine the derivative of fx equal to 2x to the 6 minus 6 e to the 2. Go ahead and pause the video and give it a try. All right, so assuming you gave this a try, this part here definitely gives us 12x to the 5. Now 6e to the 2, again, you want to notice here, is there any x? It doesn't look like it. And if there's no x, then the derivative is just 0. So the correct answer is A, 12x to the 5, because there's no x value. So this is not using the e rule. This is using the constant rule. And the derivative of a constant is always 0. Now, before we end this video, I want to give you a problem to work on that we'll solve in the next video. What's the derivative of x times e to the x? That's a good question. Maybe it's equal to the derivative of x, which is 1, and the derivative of e, which is e to the x. Maybe the derivative of a product, because this is multiplication, maybe the derivative of a product is the product of the derivatives. That feels reasonable. We remember that for limits, the limit of a product is the product of the limits. And, well, we know that derivatives are made of limits. So it feels like this should be true. But is it? Is it true? Perhaps it is, perhaps it isn't. We need an argument or some justification. So go ahead and look at these steps. Maybe write out your definition of the limit just to help get you started. We'd have limit h approaches 0 of x plus h, e to the x plus h, minus x e to the x over h. And you'd go ahead and expand and collect some terms. Right, you might need the fact that e is equal to the limit h approaches 0 of 1 plus h to the 1 over h. And see what you come up with. Maybe you're going to get 1 times e to the x, or maybe you're going to get something different. You'll have to stay tuned and find out in the next video. But please give this one a try yourself before you go ahead and click on the next video. Part of doing math, of course, is discovering and having that process of self-discovery. I really don't want you to have that ruined by seeing the answer right away. And so do your best to really give this one a good go before you go ahead and look at the solution. So for homework, you can go ahead and do the rest of the derivative power rule worksheet. Some of them had e to the x. So you're able to do those questions now. And you can also look at page 180, questions 3 to 40, and 55 and 56. Hopefully you enjoyed this video, and as always, thanks for watching.